Welcome to lecture 19 on essentials of topology. In this lecture, we will study the concept of interior and boundary of sets. Similar to the concept of closure of sets, we will see here that interior will help us to provide a characterization of open set, and also it will provide a notion of the largest open set contained in a set. Beginning with the concept of interior of sets, this is similar to the concept of closure of sets, where we have seen that how to find out the smallest closed set containing a set. What we are going to see that in a set, how one can find out the largest open set. Begin with the definition. Let X tau be a topological space and a subset A of X. Then interior of A is denoted like this one, or a circle. This is union of all G which are subset of A, such that G is an open set. Meaning is that we are taking the union of all open sets which are inside A. It means that if we are having a set X and we are having a set A, whenever we are trying to find out the interior of A, trying to take the union of all open sets inside A, and what we will get, that is nothing but interior of the set itself. From the definition itself, these are some observations. The first one is that this interior of A is an open set because this is union of open sets inside A. The second one is that A interior will always be a subset of A. From the definition, this is clear as it is union of open sets. And the third one is that we can say that A interior is the largest open set inside A. Moving ahead, let us visualize the concept of interior of sets in R2. For example, if this is a set A, then interior of A will look like in this way, that is an open set contained in the set, and note that this is the largest open set inside A. Let us take some of the examples. For example, if we are taking X as a set A, B, C, D, and let us take E, that is X is consisting of 5 elements. Take a topology tau on it, that is empty set X. This is an element, that is 2 elements set AB. Let us take this is BC. We are taking the singleton set B, and we are taking this is ABC. It can be seen that this is a topology on X. Now, if we are taking a set A, which is given as A, D, E, and if we want to find out what is the interior of A, so we have to find out union of all open sets inside A. Now see, what are the open sets contained in A? Obviously empty set is here, and if we are looking for the rest one, none of the open sets are subset of A. That's why interior of A will be an empty set. But if we are taking another set B, for example, B we are taking something like A, B, D, and let us try to compute the interior of B, that is union of all open sets inside B. So that is first one is empty set. Second is, note that this two element set AB is a subset of ABD. Even the singleton set B is also a subset of ABD. That's why B interior will be nothing but this AB. Moving ahead, let us take some other examples. Why not R with this Euclidean topology? If we are taking a set A as open interval 2, 3, what about its interior? The interior will be nothing but this open interval itself because this is the largest open set inside A. But if we are taking A as a closed interval 2, 3, what about A interior? Note that this will still open interval 2, 3 because this is the largest open set inside closed interval 2, 3. Moving ahead, why not let us take A as this semi-open interval 2, 3. What about its interior? Again, interior will be 2, 3. It is to be noted here that whenever we are taking A as semi-open interval, its interior is this open interval 2, 3. But if we are changing topology, that is if we are taking R with lower limit topology and we are computing A interior when A is this semi-open interval 2, 3, note that this interior will be this semi-open interval itself because this semi-open interval is open in lower limit topology, meaning is that the concept of this interior depends on the nature of topology with which you are working. Even on any set X, if we are taking a discrete topology, question is what about the interior of any set? So if we are taking any subset of X, interior will always be the set itself because every set is open. That's why interior of A will always be equal to A. Coming to this characterization of open set by using the concept of interior, what we say that if X tau is a topological space and A is a subset of X, then A is open if and only if A interior equals A. The first one is simple. Whenever we are taking A interior equals to A, note that A interior is open and therefore A is also open. That's why this is simple one. Conversely, let A be open, assume it, and let us try to justify that A interior is equal to A. Note that A interior is always a subset of A, and now A is also subset of A. What is A interior? We have seen that this is the largest open set inside A, and this is also given that A is the open. And from set theory, this is the largest set which is open inside A. So from here, we can conclude that A interior is nothing but A itself. One more thing is clear from here that if we are taking X belongs to an element of A interior, note that A interior is given as union of G subset of A such that G is open. So if X belongs to A interior, we say that X is an interior point of A. Now, what will happen if X is an interior point of A? So from this definition, X will belongs to some G. That is because X is an element of this union. And note that every G will be subset of A. So what we can conclude that? We can conclude that A is a neighborhood of X. Similarly, if we are assuming that A is a neighborhood of X, then what will happen? There exists an open set G with the property that X belongs to G is subset of A. And note that this G is a subset of A and we are taking the union of all such G. So from here we can also say that X belongs to union of G subset of A where G is an open set. And if this is the case, X belongs to A interior. So what conclusion we have here that if X is an interior point of A, then A is a neighborhood of X, and conversely, if A is a neighborhood of X, X is an interior point of A. So finally, we have a result with us that A is neighborhood of X, that is X belongs to X, if and only if X is an interior point of A. So this is a simple characterization. Moving ahead, let us see some results on interior of the sets. Beginning with, if we are having a topological space X tau and two subsets A and B of X, then the first one is that if A is subset of B, then A interior is a subset of B interior. If we want to justify this result, it's simple one. If we are taking X belongs to A interior, what does it mean? It means that A is a neighborhood of X. Because we have already seen the characterization, it means that B is also a neighborhood of X because B is a superset of A, and therefore we can say that X belongs to B interior. So that's all about the first one. Coming to the second one. Second one, this directly follows from the first because we know that A is a subset of A union B. B is also a subset of A union B. So A interior will be subset of A union B interior, and this B interior is subset of A union B interior. If we are combining these two, A interior union B interior is subset of A union B interior. But note that equality may not hold in general. Let us see an example. If we are taking real line with Euclidean topology, let us take a set A that is the closed interval 2, 3. Take a set B that is closed interval 3, 4. If we are looking for A union B, A union B is nothing but closed interval 2, 4. If we are computing A interior, we have already seen that this is open interval 2, 3. What about B interior? That is also an open interval 3, 4. But if we are computing A union B interior, that will be open interval 2 to 4. Now, what about A interior union B interior? That is 2, 3 union 3, 4. This is the union of two open intervals, and note that this is not equal to open interval 2, 4. Therefore, equality will not hold in general. Coming to the next one, in order to justify this result, we have to justify that A intersection B interior is subset of A interior intersection B interior, and A interior intersection B interior is subset of A intersection B interior. The first one can be directly obtained from this one because we know that A intersection B is always subset of A. A intersection B is also a subset of B. From these two, we can conclude that A intersection B interior is subset of A interior. A intersection B interior is also a subset of B interior, and therefore A intersection B interior is a subset of A interior intersection B interior. Coming to the second one, here if we are taking an element X in A interior intersection B interior, then X belongs to A interior and X is also an element of B interior. And if we are using the concept of neighborhoods, from here we can say that A is a neighborhood of X. Similarly, if we are using the same concept, we can deduce here that B is a neighborhood of X. We have already seen that intersection of two neighborhood is a neighborhood. So from these two, we can conclude that A intersection B is a neighborhood of X. And if A intersection B is a neighborhood of X, we can say that X is interior of, or X is an interior point of A intersection B, that is X belongs to A intersection B interior, and that's all about this result. Moving ahead, let us see the relationship between closure as well as interior of sets. These are two simple characterizations given in terms of complement of closure and complement of interior. So if we are having a topological space X tau and a subset A of X, the first result states that X minus of A interior is equal to X minus of closure of A, while the second states that closure of X minus of A equals to X minus of A interior. If we can prove one part, the proof of second is similar to that. So let us prove the first one. If we are looking for the first one, we have to justify two things, that is x minus of A interior is equal to x minus of A closure, and second one is we have to justify that x minus of A closure, sorry, this will be a subset. Similarly, x minus of A bar is a subset of x minus of A interior. The second one can be deduced by using the concept of interior, that is the definition of interior itself, because we know that this A bar is a closed set, and if this is closed, its complement is an open set, and if this is an open set, also we know that A is a subset of closure of A, and if we are taking the complement of these two, so A complement will superset of x minus of A bar. And now let us take the interior of both side. So this will be x minus A interior is superset of x minus of A closure interior. But note that because x minus of A bar is an open set, and therefore this will be x minus of A bar. That's why x minus of A bar is subset of x minus of A interior. Now, in order to justify the first one, let us take an element of interior of x minus of A. Meaning is that x minus of A is a neighborhood of x, and therefore there exists an open set G such that this x belongs to G is a subset of x minus of A. Note that from here, this G is contained in A complement, meaning is that we can say that G intersection A will be an empty set. Also note that X belongs to G, meaning is that G is an open set, and not only open set, this also contains X. And therefore, what we can say from here, even G minus of singleton set X intersection A is an empty set, or X is not an element of set of limit points, that is X doesn't belongs to A dash. Also, because X is an element of X minus of A, X belongs to G, X does not belongs to A. Meaning is that X does not belongs to A union A dash, or X belongs to A union A dash complement, that is X belongs to closure of A complement, or from here X belongs to X minus of closure of A. That's the proof of this result, that is x minus A interior is subset of x minus of A closure. In the same way, we can deduce this result. Moving ahead, coming to the next concept, that is the concept of boundary of sets. We have already studied the concept of closure of a set as well as interior of a set. Actually, this boundary lie something in between closure and interior. Formally, this is defined in this way, that if we are having a topological space X tau and a subset A of X, then boundary of A is nothing but, that is, the difference of this closure of A minus of interior of A. One thing is clear from this definition, because interior of A is an open set, and if we are using some simple set theory, this is nothing but closure of A minus, sorry, intersection complement of interior of A. Note that interior of A is an open set, therefore this will be a closed set, and if this is closed, we already know that closure of A is a closed set, and that's why note that this boundary of A is always a closed set. Let us visualize this concept. For example, we are taking these pictures in R2. Let us take this is a set A. We have already seen that this one represents interior of A, and this one is representing closure of A. And if we are trying to find out what boundary of A, obviously this is boundary of A, that is the difference of, or that is closure of A minus of interior of A. Let us take some of the examples. For example, if we are taking a set X as A, B, C, D, let us take a topology on it, that is empty set X, simply singleton set A, this BC as well as APC. Now, if we are taking a set A, something like this is BCD, let us see what the boundary of A means. If we are computing the interior of this set, interior of the set is union of empty set and other open sets which are inside BCD, that is BC. So interior of A will be nothing but this two element set BC. If we are computing what the closure of A, so let us see what are the closed sets. The closed sets are here X empty set, A complement is that is this BCD, BC complement is AD, ABC complement is D. Now we have to take the intersection of all closed sets containing this A, that is nothing but X intersection, this is BCD, that will be A itself, that is BCD. Finally, if we are looking for boundary, which we have already seen that this is closure of A minus of interior of A, and if we are computing this set, that will be a singleton set D. Let us take some more examples. For example, if we are taking R with Euclidean topology, and now let us take set A, that is an open interval, this is 2, 3. What about interior of A? That is nothing but the set itself. What about the closure of this set? Closure of this set is the closed interval 2, 3. If we are looking for the boundary of A, that will be nothing but 2-point set, that is 2 as well as 3. If we are taking another example in this Euclidean topology, let us take set of rationals. We have already seen that this Q interior is an empty set, while what about this Q closure? That is Q closure is R. So what is the boundary? Boundary of A is nothing but set of real numbers itself. Meaning is that all the elements of R are boundary of A. Moving ahead, these are some simple results related to boundary of a set. For example, if we are having a topological space X tau and having a subset A of X, then the first thing is that boundary of A is given as closure of A intersection closure of X minus of A, and this can deduce by using the definition plus what we have already seen, that is this is closure of A minus interior of A. This can be written as closure of A intersection interior of X complement, that is X minus of interior of A. And we have already proven that this is closure of A intersection and this is nothing but closure of X minus of A. The second result, which says that boundary of A and interior of A are disjoint set, It follows from the definition itself because by definition of boundary of A is nothing but closure of A minus of interior of A. Finally, coming to this one, this says that closure of A is nothing but union of interior as well as boundary. This is simple to justify because if we are looking the definition of boundary of A, then what will happen? This is nothing but closure of A minus of interior of A union of or union with interior of A, and that is nothing but closure of A intersection complement of interior of A union this interior of A. Now by using distributive property, this can be written as closure of A union interior of A intersection. This will be interior of A complement union interior of A. If we are looking the second one, note that this is nothing but the set itself intersection. Note that interior of A is always contained in closure of A because we have already seen that A interior is subset of A and this is subset of closure of A. So this will be nothing but closure of A with intersection with X, and that's why this will be closure of A. This is proving that boundary of A union interior of A is equal to closure of A. These are the references. That's all from this lecture. Thank you.